is that multicast is a really great technology. Streaming all across our T3 is not. So please, if you really feel the need, or if you really want to watch the conference and the speakers on your laptop, please use multicast. The NANOG webpage has links to some of the multicast drivers. Please do not stream back. The second thing is that the links to some of the NANOG slides are available, or they're becoming available as we get them, on the NANOG agenda page. So click to nanog.org, agenda, current meeting, agenda, and several of the links to the slides are there. The other big question that I've been asked quite a bit at this conference is, will I tell a joke? And the answer to that is, I don't think so. Unlike Phil, I don't think I'm a very funny person. But then Bill isn't, yeah. But be that as it may, we've got the tape. Curtis has the tape in the back. Okay, Bill, you're forewarned. Curtis has the tape. And other than that, I'll just wait one more minute to let people come in. I never introduced myself this morning. My name's Craig. I work for Merit. I'm a member of the senior research staff, and mostly I don't do NANOG all the time. What I do is involved with a number of different research projects and some other activities there. But I'm a University of Michigan staff member, as is Susan and Pam and a lot of the other NANOG staff here. And I can't think of anything else to say to kill time. No. Okay.
Don't kill time.
Don't kill time. Okay, I'm done killing time. With that, we'll go on to our next talk, which is Bill St. Arnaud, pronounced, okay, speaking about some of their experiences building the CANet 3. I don't think I know what the 2 and 1 were, but I know what the 1 was.
Yeah.
I think I missed 2 somewhere. And with that, I'll turn over the mic.
Thank you. So, for those who want to know, CANet 1 was the original equivalent to the NSFnet in Canada. CANet 2 still exists. It's our equivalent to Internet 2 in the States, and it's running in parallel with our CANet 3, our optical network. First, I'd like to introduce 2 colleagues of mine, T.W. Chung and John Coulter. These are the real technical geniuses behind this network. So if you have any questions afterwards, any particularly questions with an acronym in them, I ask you to turn them over to John and T.W. This presentation is available, or shortly should be available on the NANOG site. It's also available on the CANARIE, or CANet 3 site. There's other background papers, technical documentation on our site as well. And we also have an internet mail list on various technologies and developments in this area. It's a rapidly developing field, and there's a number of announcements by Sprint, by Frontier, and Enron, who are developing a similar type of networks here in the States. Very briefly, CANARIE is a Canadian equivalent to Next Generation Internet and Internet 2 in Canada. Very similar goals and initiatives to develop the Next Generation Internet, to propel the information highway, and so on and so forth. I won't bore you with the details. We have been now, this is our 4th generation network. As I mentioned, we funded the original Internet backbone in Canada. We built a high-speed ATM test network. Now we've got CANet 2, which is our production Internet 2 network, and now we're just starting to deploy the first optical network. And this is the first, we believe, the first Internet network that's being built from the ground up, literally from the fiber in the ground. It's being trenched in some sections to support Internet first and voice second. Almost all Internet networks today are built on a technology, particularly Sonnet, for example, that was originally designed to support voice. And we believe there's some unique characteristics of Internet traffic and its growth and so forth that we should really build from the ground up for Internet. The network's being built by a consortium led by one of our major carriers, Bell Canada, in partnership with an unusual set of suspects, Nortel, Newbridge, Cambrian, Cisco, JDS Vitel, which makes optical components, and Cambrian, which makes Metro WDM products. Key features of this network were directly coupling individual dense wave division multiplexing wavelengths directly to Cisco GSR routers. We're going to use the intrinsic self-healing capabilities of the Internet for restore and protection, and that's a major part of our research program. We're particularly looking forward, if it doesn't get too complex, to using MPLS to do layer 3 restore and protection. We're going to completely bypass all the traditional telecom services, SONET and ATM, for this network. This is the network that's being deployed. The Ottawa, Toronto, Montreal section's now up and running. It's been running for about a month. The rest of the network will be completely up and running in the spring of next year. It is currently 2 OC48s, but we have 8 wavelengths reserved for us. Like the US here, the network interconnects a number of gigapops. And these gigapops are all up and running now, connected to CNET2, and they in turn interconnect to high-speed regional networks in each one of our provinces. In addition, each one of those provinces now are starting to deploy optical regional networks in partnership with a local cable company or a local carrier, and that will interconnect to our optical backbone. So it's about 7,000 kilometers running from Vancouver to Halifax, and we have ATM connections to St. John's and Charlottetown. We are routing through the States for a portion of this network to the facility called the StarTap. That's the Ameritech NAP switch, but a portion's been segregated off, as you know, for the Internet 2, next generation internet networks like the VBNS, Abilene, and so forth. And the StarTap stands for Science, Technology, Advanced Research, Transit Access Point. So we will be the first to go in there with OC48 to optical connections. Why are we doing this? Well, there's a big driver, and everything really comes down to money. And one thing, we've done a detailed financial analysis, and we believe that with an optical internet, you can substantially reduce the cost of internet delivery. Currently, the traditional OC48 SONET network, if you're running IP over that, costs vary between the $4,000 to $5,000 per kilometer per year. Now, this is just your infrastructure costs. This is before overhead maintenance, most importantly, profit. So you've got to mark that up, usual telco markup 100 times. Optical internet, we believe, with today's technology, using equipment we can get today, costs about $500 to $700 per kilometer per year on long haul. With the new low-cost regens, the new 10x gigabit Ethernet, low dispersion fiber, long-range optical amps, we believe that the cost will drop to about $100 to $200 per kilometer per year next year. And we even believe there will be more dramatic savings in the metro or local loop market area with the new Metro WDM products from Sienna, Cambrian, Nortel, and so forth. In that case, our analysis, we believe, on a cost basis, that we can deliver an OC48 cheaper than we can deliver a T1. Because we're completely eliminating all the DACs, all the SONET muxes, all that equipment's gone. It's just a simple optical add-drop mux, passive device, and you can have multiple 32 channels, each at OC48, protocol bitrate transparent in your metro area. Very, very simple and very easy to implement. Here's an abstract diagram of the network linking. It's showing the fiber routes we're using for the network. We are sharing a single fiber with the carrier, and we have 8 wavelengths dedicated to ourselves for our optical internet project, and the carrier is using 4 wavelengths for their traditional SONET service, for their traditional ATM and voice and TDM services and so forth. And they, of course, are using what are called SONET BLSR rings. We are just using a single path currently on the network. So we are, in this current design, have many points of single points of failure, but we're working in parallel with CNET2, our ATM network, and we'll have route diversity and restore by combining an ATM network with an optical network. I'll talk about that in more detail. 2 key features that we think an optical internet will address. One is that you've heard about the fractal or burstiness of an internet. Huge bursts, traffic doesn't aggregate. We're going to use both sides of a fiber ring and absorb those bursts rather than trying to buffer them out. And the average peak to average load on an internet link is much lower than a traditional telecommunications circuit. And so with high bandwidth optical links at low cost, we can absorb these very bursty traffic characteristics of the internet. The other major characteristic we can do with an optical internet is take advantage of the asymmetric loads. There's been several discussions on the NANOG recently, and many of you experience this, where there's many links are heavily congested in one direction and lightly loaded in the other direction. Well, traffic engineering individual wavelengths, we can optimize the physical network to take advantage of the asymmetric traffic loads presented to us from the various routers. This is just an example case showing from a big web farm how you'll have heavy loads in one direction, and conversely, at the consumer end, the traffic being asymmetric loaded in the opposite direction. This is a traditional architecture we're all familiar with. This is the way most internet networks are currently engineered. You have a router into an ATM cloud, merged with other ATM services. That ATM switch will be muxed into a SONET MUX terminal where other TDM services will be muxed in. And then finally, that's all brought into a SONET transport terminal, which is connected to a SONET ring. Between the two SONET terminals, you usually have a fiber ring, a working fiber, and a protection fiber. One side of that fiber sits idle all the time, waiting for that inevitable backhoe. And so half your bandwidth is sitting idle, waiting for once a year for a backhoe to come along. And that's the traditional telco architecture as we know it today. Well, this is what we're building. We're bypassing all those layers, all that equipment that's in the traditional telco structure. And we're coupling the routers directly into what's called the wave division multiplexer into the fiber. Now, wave division multiplexer is just a passive device. It's usually a Bragg filter. It's a little box which has many ports for connecting all the 1310 fiber. On the output, it puts it all into a single or multiple colors on a single fiber. And what we can do then, we can structure the wavelengths and optimize the design of the wavelengths for our traffic loads. And this just is an illustrative example. We have 5 wavelengths going from right to left and 2 wavelengths coming in the opposite direction. And this is assuming there's heavy traffic load from right to left. Also are using simultaneously both the working and protection fiber. We don't want to let that fiber go to waste. And what we want to do, this is part of our research program, is when we get a fiber cut, we will then use quality of service and flow control to throttle back the traffic load in the event of a fiber cut, rather than doing path protection switching that is traditionally done today. And so we believe, particularly given the high burstiness of the internet and so forth, that we can implement this and use what's called layer 3 restoral techniques, prioritize traffic and so forth for customers that have a service level contract and flow control everything else back. The other nice thing we can do now with that protection fiber that's sitting idle, we can do something that's called cut-through wavelengths. On the upper fiber going across Canada, we can do our traditional hop-by-hop routing. We have 2 pair wavelengths, standard stuff, just hop by hop. But what we can do on the protection fiber, which is sitting idle, is set through cut-through wavelengths. So for example, from Vancouver to, say, a U.S. gateway, we find high traffic volumes, we can set up a wavelength that goes directly from that gateway all the way to Vancouver without going through a single layer 2 device, without going through a single layer 3 or layer 2 device, ATM switch or a router. So it gives us the most efficiency and the least latency and queuing delay, because obviously there's no queuing. And so you can traffic engineer your networks in any way that's the best optimum way to support your traffic flows and for any match of source and destination pairs. Now another big area of our program, as I said, is layer 3 restoral. The internet IP network is intrinsically self-healing. And we know if we crank down the timers on the routers, we can get down to restoral speeds close to what's advertised in SONET. Now, there's a little white lie the carriers tell you that SONET restoral speed is 50 milliseconds. Well, that is only true if you have what's called a 1+1 restoral ring. It is not true if you have a node failure or if you have a more complex SONET network, which is common today, and it can be several seconds to have a SONET restoral. We believe we can achieve that in an IP network, but the biggest problem is announcing the routes. That's what takes the time when you do have a network linkage problem. So we hope to use MPLS. We're just getting some beta code now from our vendors, and we want to use that to give us that fast restoral. We also hope will give us the ability to do some traffic engineering and other capabilities as well. So with layer 3 restoral, we've got a lot more flexibility than the traditional layer 1 restoral capability. It's a lot more intelligent. You can offer a hybrid mix of services to your clients. Some clients don't need restoral protection. Many internet links today are not on SONET restoral links. Some clients, like voice telephony, you want to restore it as fast as you do on traditional SONET networks. And that's the things, you can give this a variety of services, and you can have diverse restoral paths. You don't have to go just on the opposite fiber. You can route all sorts of different directions. So that's a major part of our program, which we'll be implementing in the spring. Now, one of the big areas I think is a significant advantage is in the metro area. As I mentioned, there's several companies who are developing metro WDM products, Ozycom, Cambrian, Sienna, Nortel, and so forth. And this is a totally passive product, or doesn't use any active components, and you have these optical add-drop muxes. So in a fiber ring up to about 100 kilometers, you can have up to, right now, 32 different wavelengths. Each one of these wavelengths can work up to OC48 speeds. But the nice thing about it, these systems are called data transparent. You can use any protocol or bit rate that you want. So you can use packet over SONET, you can use ATM, you can use gigabit Ethernet, you can even use analog video. It's the same connector. So you plug in your device, your LAN, the same connector, and it's completely transparent to the signaling layer what technology or what protocol you're using. So it's a very, very attractive way of delivering local loops or providing service within a community. In this example, we have cable modem MUX, for example. This is a company called Ozycom that's developing this technology to solve the return channel bandwidth problem on cable modems, is they now put on a wavelength on your cable system, and then you get rid of the noise and the bandwidth problems on cable modems. Similarly, people working on for DSL, DSLAMs, rather than use an ATM circuit, you use a separate wavelength to haul back your DSLAM muxing service. And you can have multiple ISPs connected to this ring, each with their own set of wavelengths, each with their own set of mesh circuits to their various customers, major institutions, and so forth. A 32 wavelength system, depending on how it's configured, you can have up to about 150 pairwise connections, each with their own individual wavelengths, each up to OC48. So it's a very, very exciting technology. Now, as one variation of this, we're in discussions with Ameritech and with some people in Chicago about building an optical internet exchange. Again, using this technology, we can set up pairwise, or we're going to have, well, let's first pairwise wavelengths, each up to OC48, but each with their own protocol, whatever the recipients want on each end, and set up all these pairwise connections between the various ISPs. But as well, we can have a common layer 3 device if we want, and they can set up wavelengths to a common layer 3 device if they want to do that, peering them that way. So it allows a mixture of services and allows different protocols. In this example, we have one ISP that's running an ATM connection, another ISP that's running Ethernet, another one's running packet over SONET, and so forth, all in the same fiber, each running their own protocol independent of the other, and they can switch at any time, and they can switch their bit rate. You may want to first start off with just a simple Ethernet connection. Without talking to anybody, you can change that to a gigabit Ethernet by just plugging in a gigabit Ethernet. It's that simple. And that's the power and attraction of this technology. This is just a logical diagram. One of the nice things, again, is you can engineer the wavelengths to take advantage of asymmetric flows. There's been discussion in ANOG of problems of big web farms with huge flows one direction to various ISPs. Now, ignoring some of the peering issues and so forth, but this allows to optimize the network from a traffic viewpoint to take advantage of those traffic flows in certain directions. And you can configure these very easily and simply on a WDM network. Now here are some of the components of an optical internet shown here. What we have is it's combined with a traditional carrier SONET network. You have your SONET transport terminal on the top corners, and then we have the routers. Now the routers go into a device called a transponder. The carrier needs that to isolate the power levels and the light levels of the router from the other light levels. The optical amps scattered along the network are very, very, very sensitive to any fluctuation in power levels. 1 dB change will throw out everybody. So of course, since they're carrying their TDM traffic in this same fiber, they insist on having what's called a transponder to isolate and lock in the frequencies for your wavelengths, which they control. Now, we are using currently a Nortel Regen box for that, but there's new devices out, both just little chipsets from a number of companies that will replace the larger Regen box. And so we go from the router through the transponder into the WDM multiplexer, that wedge-shaped device. Again, that's just a small passive device, it's like a prism, no active components. And then we go through up to about 250 kilometers through a number of optical repeaters. These are broadband iridium-doped amplifiers, and they amplify all frequencies together. But after about 250 kilometers, you have dispersion effects, you have attenuation effects, and depending what type of fiber, there's a number of other problems arise, so you have to go back to the electrical level to clean up your signals and so forth. Right now, the only way to do that is to use sonnet framing. So we're currently using sonnet framing on this on long haul, and then we go to the electrical level to do 3R regeneration, reclocking, retiming, reformatting, and so forth, and then we go back into the optical domain out to the far end to the router. Eventually, we hope next year that we can use a less expensive type of regeneration using 10x gigabit Ethernet and other techniques that are coming from the manufacturers. Some of the things we've been testing this network now, and we've gone through some exhaustive interoperability tests. What we do, we have a Cisco router which provides all the clocking and syncing for a span, and then the regens and the other routers drive off do the clock recovery from the Cisco router. We're using the new Cisco OC48 cards. They're an EFT card, so some of the issues, everything works fine, but we did run into some small problems, but we must make clear it was an EFT card, and we're expecting a production card shortly. One thing we discovered is Sonnet is not an interoperable standard. You go to different vendor manufacturers, and there's always little problems between how they interpret various signaling codes and so forth. And we had to do a little bit of work with the vendors to get that sorted out. So we did all sorts of alarm testing, component failure, static routes, and so forth, and all the various routing policies and so forth. And we managed to do traffic loading tests, but we couldn't fully exercise the cards because it's difficult to find testers that work at OC48, particularly packet over sonnet testers. But everything works fine, and the network's been running now for a month. This is an example of the test and some of the issues we ran into. One of the things we discovered is that Sonnet was designed to be a contiguous layer, and everything else is right on top of it. When you start breaking up Sonnet links, you run into some interesting problems in terms of network management and so forth. And we had to put these digital cross-connect cables in around the router so that we can look and have a management view of the regenerators going across the country. And we can talk about some of the issues ongoing there in terms of isolation, testing, and so forth. We start breaking up Sonnet links and clock synchronization and so forth. But they're all solvable, is the good news. So test results so far in the network, as I said, Sonnet implementations are not interoperable if you're working at the Sonnet transport layer. Most of the packet over Sonnet implementations, the router is connected to a Sonnet add drop mux, and that's not a problem. And that's what, the sprints are doing that and so on and so forth. When you break right into the fiber and using Sonnet regen, it does cause problems, but they are solvable. Throughput testing, I say, is still a problem for us. We're waiting for some packet over Sonnet test sets and some of the new 10x test sets, and they're absolutely essential for doing throughput testing and load testing and so forth. And that's been one of our problems. We haven't really yet been able to exercise the network in terms of those speeds, OC48 or OC192, because we haven't been able to get test sets that can generate that type of traffic. Now, one of the things we're looking forward to doing is working with some new gigabit Ethernet because we believe will significantly reduce the cost. Right now, this is using Sonnet framing, although we're not using a Sonnet network. But in the regional networks, we expect to be using pretty well exclusively gigabit Ethernet, and also the new 10x gigabit Ethernet that's coming out next year, which clocks out close to OC192, about 10 gigabits per second. And there's some real advantages to that, because gigabit Ethernet, as you know, was designed for the data world, came from the data world, and has nice, simple segmentation reassembly. You don't have all those issues, and so on and so forth. Right now, though, gigabit Ethernet is not very efficient for long haul. It uses 8-bit, 10-bit block coding, which is even less efficient than ATM. But we're looking forward to the new 10x GBE, which we think will be a lot more efficient. And so it gives us a lot of advantages. There's still packet over Sonnet. That is a well-established standard. We know it works. It can be used in Sonnet networks. But there is some issues. As I mentioned, Sonnet's not an interoperable standard. It's very difficult for the manufacturers. It's really challenging to build OC48 or even OC192 segmentation reassembly chipsets. And so that's a big challenge, whereas gigabit Ethernet we think will be easier. But the big advantage is in tributary services. One of the big problems many carriers experience is, Or your customer's experience is, the customer says, I see them digging fiber in the road across the street from me. Well, I'd like to connect to that and get an OC12 or OC3 or DS3 service. And the carrier says, well, no, we have to backhaul you to the CO, because to do that, they have to drop in a SONET add drop mux. It costs $1 million to drop off a simple tributary service. With gigabit Ethernet, we can drop in just a gigabit bridge device or even a simple router, and we can backhaul in a separate set of wavelengths to a major router. And so we've already experienced this with one of our major institutions. They were in one city, and the fiber big CO terminus was in another city. And previously, the carriers say, well, we'll have to backhaul you in copper, a DS3 link or whatever. But now they discovered, well, now that we don't have to put in a SONET terminal and a SONET mux, we can just drop in this bridge. It's much, much simpler and cheaper for us to do that, and that's what we're doing. So that's going to be a major advantage now with gigabit Ethernet and getting away from the SONET transport nodes. So this is our program coming up. We will be deploying, we've got now 2 times OC48 working in central Canada. We'll have that fully deployed across the country this spring. We're going to be doing route diversity and layer 3 restore in parallel with our ATM network, sort of a hybrid mix of architecture. This is how we're going to provide protection. But we'll be starting up active program, research program, and testing using fast restore and splicing routing with MPLS and quality service with DiffServ. John's taking the lead on that program. And we have William Matten here who's also working on our MPLS. We hope to have details on our optical internet exchange in the 3rd quarter of this year. And we expect to have our gigabit Ethernet over WDM deployed in a couple of our metro areas in January or February. The additional wavelengths, the other 6 wavelengths we want to use for the new 10xG BE, we think there's a lot more advantage to that than using packet over SONET. And we'll have our cut-through wavelengths in the 4th quarter next year. And using both sides of the fiber ring as well will be in the 4th quarter next year. So that's basically our program. We're quite excited about it. I think the announcements by Enron and Sprint and Frontier Globe Center to support the evidence that the cost savings here are quite dramatic, the potential to deliver really high bandwidth at a very low cost to the customer. I suspect we're on a major cusp of a revolution in terms of delivering high-speed internet to our customers. Thank you. Got time for questions?
You mentioned that one of the great advantages of this was to be able to have fiber with strongly differentiated amounts of traffic going back and forth to, say, a web farm where you have very small request packets, very large response packets, and very highly differentiated packet traffic then. How easy is it to reconfigure one of these things if that switches? Say you have an event like a John Glenn goes up in space and all of a sudden all the traffic is going to that service provider, PSI at shuttle.nasa.gov, and then all of a sudden PSI's traffic is coming somewhere else. Can you easily reconfigure that so that the sizes that you're allocating can dynamically change, or is that something you have to fairly manually do at this point?
Right now, it's worse than manual. A lot of this technology has to be pre-configured in the factory. Now you can get a module. You get the card that's set up, and you slap in the module, and you do it that way. But it's not dynamic at this point. Now, a lot of researchers are working on optical cross-connect switches, which are dynamically configurable, but that's 2 or 3 years down the road yet. But just in terms of the smallest channel is an OC48. So you have your turn channels in OC48, and you may have 3 forward channels. That's the granularity we talk about now in the WDM world.
You half answered my question, which is where the heck are you going to get the traffic from to test out traffic engineering options and so forth? And I heard you say test sets. I would assert that it's completely uninteresting to look at anything other than heavily aggregated TCP traffic, and preferably microflows. So this sort of re-raises the question of how are you going to test traffic engineering in such a way that people can judge whether it's more useful than simply adding more bandwidth here and there, parallel OC48 paths, and then do something like Curtis's multipath stuff, or doing some kind of load balancing point-to-point or whatever. What's interesting is if you have your concept, which is you take 2 greater than half full lines running in parallel across the country, or whatever, what have you, and then doing a path collapse so that everything ends up on one line. And especially when your delay bandwidth product is that size, you want to see how everything sorts itself out and whether or not any kind of fancy queuing or what have you has any use. So I would tend to assert that test sets themselves aren't so useful, and what would be more interesting is trying to figure out ways of getting end users of yours, the research community, the universities who are doing porn browsing or what have you, to figure out how that they can, UBC to University of Toronto is sort of interesting, UBC to McGill is sort of interesting, and so on and so forth. Test set where you're doing just generation of random frames seems really uninteresting.
I agree 100%. The test sets only serve as initial testing for loading and so forth, because you've got to have real traffic and you've got to see what the bandwidth delay issues are and so forth.
The other thing that would be really interesting is if you could work out some way to record the traffic in any way, shape, or form so that it could do offline analysis.
Trying to record OC48 is a challenge.
Of course it is. But you have the research money, it seems, and CANARIE seems to be turning into something other than just a loud bird with a nice song and pretty feathers.
We don't get jokes about it.
Yeah. If there's some way to actually ship traffic to the likes of the people at LVL and so forth, that would be very interesting.
Yeah, we work very closely with the internet community and the NGI, and yes, we want to do those things.
Yeah.
Our problem in Canada, I think, if we aggregated all our university traffic and put in one pipe, we still wouldn't get over 50 megabits.
Sure. I mean, basically everybody else is having the same problem too. STM16 just isn't interesting, or is rather difficult to test because nobody has enough traffic to fill any of these things, even with the TTM problems with the EFT cards and so forth. Basically, you're the people who have the transparency to actually talk about what you're doing. The rest of us who are actually building this stuff in parallel either have commercial concerns or NDAs at the eyeballs.
Yeah.
So if you're able to take advantage of the fact that you're in a position to exploit your transparency, that would be more than welcome. And I would retract some of the things I've said historically about your gang.
Okay. Thank you. Yes, we intend to do all those things as much as we can within limited budgets.
Any other questions?
Again, if all the information there is on the website and background papers, we have a big background paper that describes some of the architecture and engineering details in more detail. Okay, thank you. Yeah.